This is N.K. Rana, Department of Physics, Jain College, Ranchi. This audio lecture is on Special Theory of Relativity, part of mechanics paper in semester 1 for Physics Honors course. In 1905, Albert Einstein showed how measurement of time and space are affected by motion between an observer and what is being observed. Relativity connects or unifies space and time, matter and energy, electricity and magnetism. These concepts are also a key to the understanding of the physical universe. The first important thing is to understand what we mean by motion. When we say that something is moving, what we mean is that its position relative to something else is changing. For example, a passenger moves relative to an airplane, the airplane moves relative to the earth moves relative to the sun moves relative to the galaxy of stars, and so on. In each case, a frame of reference is part of the description of the motion. To say that something is moving always implies a specific frame of reference. So what is a frame of reference? An inertial frame of reference is one in which Newton's first law of motion holds. In such a frame, an object at rest remains at rest, and an object in motion continues to move at constant velocity if no force acts on it. Any frame of reference that moves at constant velocity relative to another inertial frame is itself an inertial frame. All inertial frames that can be described are equally valid. So what is a frame of reference? An inertial frame of reference is one in which Newton's first law of motion holds. In such a frame, an object at rest remains at rest, and an object in motion continues to move at constant velocity if no force acts on it. Any frame of reference that moves at constant velocity relative to another inertial frame is itself an inertial frame. All inertial frames that can be described are equally valid. Suppose we see something changing its position with respect to us at constant velocity. For example, let's assume we are on a train and see trees passing by. So we can ask whether the trees are moving or the train is moving. However, these questions are meaningless because all constant velocity motion is relative. There is no universal frame of reference that can be used everywhere, and no such thing as absolute motion exists. So we can say that the theory of relativity deals with the consequences of the absence of a universal frame of reference. There are two postulates that are the basis of the special theory of relativity. The first principle of relativity states that the laws of physics are the same in all inertial frame of reference. This postulate follows from the absence of a universal frame of reference and the fact that all frames of references are equally valid. The second postulate states that the speed of light in free space has the same value in all inertial frame of reference. This speed of light is 3 into 10 to the power 8 meters per second. This postulate is based on the negative result of the famous Michelson-Morley experiment. To understand the profoundness of this postulate, let's do a hypothetical experiment. Suppose a person takes off in a spacecraft with a velocity that is half the speed of light, and another person standing on the ground turns on a searchlight as the spacecraft is flying past. Now let us assume that both the persons measure the speed of light coming out from the searchlight using identical instruments. The person on the ground finds the speed of light from the searchlight to be 3 into 10 to the power 8 meters per second as expected. But the second person, who is traveling with half the speed of light, according to common sense, should find the speed of light slower compared to the person on the ground. But he also finds the speed of light from the searchlight to be same, that is 3 into 10 to the power 8 meters per second, even though he is moving parallel to the light waves with half the speed of light. What this implies that particles of light, that are photons, travel with the same speed for any observer regardless of their relative motion. This result can be explained only by taking into account that space and time are not absolute and they depend on the relative motion between the observer and what is being observed. In simple words, the time and length for one observer is not same for the other who is in relative motion. Before Einstein's work, a conflict had existed between the principles of mechanics, which were then based on Newton's law of motion, and those of electricity and magnetism given by Maxwell. The Newtonian physics could not explain the consistency of speed of light. Einstein showed that Maxwell's theory is consistent with special relativity, whereas Newtonian mechanics is not. And this modification of mechanics brought the two branches of physics into agreement with each other. Relativistic and Newtonian mechanics give same results for low speeds. At higher speeds, Newtonian mechanics fails and must be replaced by relativistic version. As consequences of relativistic mechanics, the time slows down for objects in motion, while this effect is not noticeable in everyday experience. It becomes apparent at speeds approaching the speed of light. This phenomena is called time dilation. There were a number of experiments conducted in which an atomic clock on fast moving planes showed time moving slower than atomic clocks stationary on the earth. This shows that time is relative. Time slows down for objects approaching the speed of light. It is important to note that time dilation is relative to the perspective of the observer. An observer in the space with clock would not notice time dilation. Everything would seem normal to him. However, for an observer on the earth will observe time dilation in the clock placed on the moving ship. The time in the clock's frame is called proper time and is denoted by T naught. The relative time T observed by the observer on the ground or the earth is given by the relation T is equal to T naught divided by root over 1 minus v square by c square, where v is the relative motion between the observer and the observed, and c is the speed of light. Similarly, another phenomena of length contraction happens where the proper length to an observer on the ground appears shortened due to its relative velocity. That is all for this lecture. We'll continue in the next. Thank you.